Okay, so hi everybody. Again, due to technical difficulties, the recording got corrupted. I'm post-recording the same lecture again. And let me remind you what we did on Wednesday. First of all, we were studying, well, we have been studying root systems for a while. So in the root system phi, we have this kind of, the most important condition is that S alpha or beta is equal to, well, belongs to my root system phi for all roots alpha and beta. So whenever you have two roots, you reflect one with respect to the other, and then you get the root as well. And there is also a related concept was of Coxeter groups. And these are the groups that are defined combinatorially, subject to the condition that Si is j to the Mij is equal to the identity for all I and j in your indexing set. So it's a group defined by generators and relations. And the formula for a reflection of a root beta with respect to alpha was given by beta minus twice the ratio of two dot products alpha beta and alpha alpha. And so the condition that the root system is crystallographic was that this integer, that's supposed to be times alpha. So this integer, this number is supposed to be an integer. If twice alpha beta divided by alpha alpha is an integer for all roots alpha and beta. And so this lecture I want to study these crystallographic root systems. In general, previously we studied arbitrary root systems, but now I'm going to focus on the crystallographic ones. And by the way, at the beginning of the lecture I got asked whether how is this all related to cluster algebras, because I've been talking about root systems for several lectures and the connection is not clear. And that's the beauty. In the next lecture I'm going to explain the connection to cluster algebras, and it's just going to be a direct kind of equivalence, which is crazy because at this point it's completely invisible that the relation is that there's going to be any relation. Now I want to introduce an important invariant of a crystallographic root system, which is called the Cartan matrix. The Cartan matrix A of a root system, of a crystallographic root system phi, is given by, so it has entries, it's a square matrix with entries Aij, where the rows and the columns are indexed by simple roots. And so the ijth entry is just the same integer that you get here. So it's twice the dot product alpha I, alpha j divided by alpha I, where we choose some simple system delta. Alpha 1, alpha 2, all the way up to alpha r is a simple system. Okay. So you choose a crystallographic root system, then you choose a simple system. There's many ways to do that. You can permute the entries, so you can also choose some different sets of simple roots, and that's gonna a priori give you different matrices, different Cartan matrices. But anyway, you're gonna get an integer square matrix for each such choice. And actually, let me mention that the actual result almost doesn't depend on any of the choices. It only kind of depends on the root system. And more precisely, claim the Cartan matrix depends only on the root system phi up to a simultaneous permutation of the rows and columns. Because, well, if you permute the entries of the simple roots, then that corresponds to simultaneously permuting the rows and the columns. But up to that transformation, the Cartan matrix is uniquely defined. So in other words, if you choose some other simple system, then because any two simple systems are related by a unique element in your reflection group, and such elements are isometries, you get that the entries of the Cartan matrix don't really change when you switch your simple system to some other one. Okay. And now I guess this is a good place to explain the low dimensional examples. So I'm going to be explaining examples of rank 2. So here the rank is just the number of simple roots, or in other words, the dimension of the span of my root system. And so if the rank is 2, then my root system is going to live in the plane. And the way to try to come up with these examples is usually I can start with some regular 2n gon. So let's say I start with a regular square, well, just with the square, and then I just draw the origin and I draw the roots to the vertices of the square. And then for the square, it turns out that the answer is not interesting, because this, well, you can stop the video and think about what is wrong. We have some kind of standing assumption on root systems about what is wrong that is not satisfied for this root system. And the answer is that this guy is not irreducible. This is not an irreducible root system, because it's a union of A1 and A1, which are, so A1 looks like this, and then I just take two orthogonal A1s, and therefore this is not irreducible. Okay, so the square is not interesting, but the hexagon is not only interesting, but something we already saw before. So here is my interpretation of a regular hexagon, and then if I draw the corresponding roots, then that is a familiar root system of type, so this is a root system of type A, and so it corresponds to the symmetric group of permutations of in S3, but then this index here of any root system is always going to be the rank. So the subscript here is the rank. So that's always, in the plane, that's always 2. Okay, now if I take the root system, the A2 root system, and then I want to compute the Cartan matrix, which is given by this condition. So it's, first of all, it's going to be a square matrix of size 2, because it's rank 2. So A is a 2 by 2 matrix with entries Aij given by twice alpha I, alpha j, divided by alpha I, comma alpha I. And if you, well, first of all, Aii is equal to what? You kind of, if I is equal to j, then these two things just cancel out, and then you get 2. So the diagonal entries of any Cartan matrix are just 2, 2, 2, 2, 2. So here I'm going to have 2 2's. Okay, but what are these off-diagonal entries? For that I have to choose the simple roots, and there are many different ways. Let me just randomly decide that this is alpha 1 and this is alpha 2. And then I can compute the, well, I can choose the length of all roots to be, let's say, 1, and then the denominator is 1, but the dot product of these two guys is negative 1/2. So the entry is going to be, the entry of the Cartan matrix is going to be negative 1 here and also negative 1 here. And that's the answer. That's the Cartan matrix. Now, let me, instead of trying the hexagon, I'm going to ramp it up and try the regular octagon. So that is a root system, but there is a problem with this example. If you try to look at this condition, then you can see that this root system is not crystallographic. And that's a problem. I want to classify, I want to only look at crystallographic ones. Why is this not crystallographic? So what is this crystallographic condition really telling you? It's telling you that this number is an integer, but what is this number? This number tells you that if you choose some root, let's say you choose a root alpha, and then you choose some other root beta, and then you reflect beta with respect to the hyperplane, well, in this case the line orthogonal to alpha, and you get some other guy which is S alpha of beta. And then the condition, this coefficient here, is the number of times you need to add alpha. So you need to add a multiple of alpha, kind of number of copies you need to add alpha, subtract alpha from beta to get to S alpha of beta. That's the entry of your Cartan matrix. And so that has to be an integer. In particular here you see that the angle is 45 degrees, so if you let's say this is alpha and this guy is beta, so you want to reflect beta with respect to alpha, you get some other root here as alpha of beta, and then as you count the number of copies of alpha to add to beta, you get that that's like square root of 2 times alpha. So that's not good. Square root of 2 is not an integer. But then I'm going to fix my root system by changing the lengths of the roots in a clever way. So what I'm going to do is I'm going to draw a square. And then I'm still going to draw 8 roots, but they're going to have different lengths. They're going to go to the midpoints and the vertices of the square. Okay, and now this guy here is crystallographic. You can check this if you choose, like if you want to, let's say you want to reflect this root with respect to this line, you get to this root here, and that's going to be exactly 2 copies of negative alpha. So if you want to reflect the long root, you're going to add 2 copies of alpha. If you want to reflect the short root with respect to some line corresponding to the long root, then you're going to add exactly 1 copy of the long root. So this is crystallographic. And that root system is usually denoted B2, and the corresponding Cartan matrix, again, it has 2 on the diagonal, but then remember this Aij is the number of copies of alpha I need to add when I reflect beta with respect to alpha. And as we saw, for the long root I need 2 copies, but for a short root I need only 1 copy. So the entry is, well, and it's negated because it goes in the opposite direction. goes in the opposite direction from alpha. So the off-diagonal entries are negative, and in this case they're given by -1 and -2. In particular, the Cartan matrix is not always symmetric. This definition is not invariant when you swap I and j. Alright, so the next stop is a Tangon, which is not going to give you any crystallographic root system, but the next stop is actually interesting. So let me draw one more root system of rank 2. And what I'm going to do is I'm going to draw an equilateral triangle and another one that's upside down. And then I'm going to choose the origin and I'm going to draw all these vectors. So my root system is going to have 12 roots. And that root system is called G2. It is a crystallographic root system, which is not exactly trivial to check. Let me fix this vector a little bit. So let me try to check that it's crystallographic. So we basically have these long roots and short roots. And let's say I choose a short root alpha, and let's say I choose some long root, let's say I choose a long root beta. And then if I reflect beta with respect to alpha, I'm going to reflect it along this line, so that's going to be, that guy here is going to be S alpha of beta. And the number of copies of alpha I need to add to go from here to here is 3. So 1, 2, and 3. On the other hand, if I wanna reflect alpha with respect to beta, then I need to reflect it along this line. So this guy here is going to be, this guy is going to be S beta of alpha. And the number of copies of beta I need to add to get from alpha to its reflection is just 1. Well, -1. And that's it. So the Cartan matrix, first of all, the conclusion is that this is a crystallographic root system, and the Cartan matrix is given by, it has a -1 and a -3. And that's it. So it is not hard to check that whenever you have a root system of rank 2, then let's say you have 2 roots, alpha and beta, and then you know that this number is an integer, so twice alpha comma beta, or alpha is an integer, and also the symmetric number twice alpha beta over beta is also an integer. And if you look at this angle here, then these two conditions put some heavy restrictions on the cosine of that angle, and therefore, well, anyway, exercise check, and that there are no more root systems, no more crystallographic root systems of rank 2. So we have somehow classified the only possible entries are G2, B2, A2. These are the irreducible ones, and there's also a reducible one, A1 times A1. Now, with this classification in mind, let me characterize all possible Cartan matrices. So I'm going to state a certain proposition which is going to say that Cartan matrices satisfy certain properties, and then these properties characterize Cartan matrices. Okay, so a square matrix A is a Cartan matrix of a crystallographic root system. Well, let me write of some crystallographic root system phi if and only if. So this is a pretty strong statement. A pretty strong statement. It goes in both directions. If and only if it has the following properties. So the first property, as we discussed above, is that aii is 2 for all I. And the second property, right, on diagonal we have the 2's, and the off-diagonal entries have to belong to the set aij, belongs to the set 0, -1, -2, and -3. This is for I not equal to j. And also, okay, so we saw that the matrices, let me show the matrices. The matrices are not quite symmetric, but there is something symmetric about them, which is that the off-diagonal if some off-diagonal entry is 0, then the corresponding two roots are orthogonal, and therefore the symmetric entry also has to be 0. Aj is also 0. So the zeros in the Cartan matrix are symmetric. Now another condition which comes from the above classification in rank 2 is that if aij is not -1, so if it's either -2 or -3, then the symmetric entry has to be equal to -1, as we saw in all these matrices. If you have -3 here, then the other entry is -1. And so these are the conditions on the off-diagonal entries. And then there's two more global conditions. The first one is that the matrix A is positive definite, which let me remind you of a simple condition to check that the matrix is positive definite, which is if you have a matrix A, so this here A, then you can look at the principal minors. So just like the top left entry, then the top left 2 by 2 minor, top left 3 by 3 minor, and etc. of a square matrix. And the condition is that A is positive definite if and only if all principal minors are strictly positive. So for instance, for these matrices here, the top left entry is always 2, and the determinant of the whole matrix is, well, here it's, for this matrix, it's 3, and then 2, and then 1. So the determinant is always positive of any Cartan matrix. And the reason this is true for Cartan matrices is because they encode these dot products. If you choose any basis and you write down the matrix of dot products, that's called the Gram matrix. It's always positive definite. Finally, the last condition, which is going to be also important when we come back to cluster algebras, is that A is symmetrizable. And what is symmetrizable? Symmetrizable means that there exists a diagonal matrix D with positive diagonal entries. Such that D times A is symmetric. So why is it true that a Cartan matrix always is symmetrizable? If you think about it, you look at the entries of your Cartan matrix, then you see that even though this is not symmetric when you swap I and j, if you kind of multiply each row by the denominator, then the result is going to be symmetric. So for Cartan matrix A, you can set D to just be equal to the product of alpha 1 on the diagonal matrix with whose entries encode the squared lengths of these simple roots and zeros on the off diagonal. Right, so it's easy to check that if you multiply A on the left by this matrix D, then the entries are going to be just twice the dot product of alpha I and alpha j, and then that matrix is just literally going to be the Gram matrix. So it's positive definite and symmetric. Okay, and so alright, now this is a number of conditions, but as we just saw, all of these are easy to see just from the properties of root systems. But what's hard to see is that if these properties are satisfied, then there is some crystallographic root system such that its Cartan matrix is given by this matrix A. So this is a kind of beautiful result which allows you to reduce the problem from geometry to kind of combinatorics, right? You just need to find all matrices satisfying these conditions. Okay. You go through all possible options and then you check that the result is positive definite and symmetrizable. Which still doesn't seem completely trivial, but we're actually going to classify them pretty soon. And one other thing I want to mention is that I want to say that the Cartan matrix of a root system is kind of a complete invariant. So another proposition is that two root systems have the same Cartan matrix if and only if they are related by an orthogonal change of basis. And prime are related by a, let me just write by an isometry. So in other words, literally as collections of vectors in the Euclidean space, they are, you can kind of rotate one into the other or reflect or something like this. So in other words, classifying crystallographic root systems is the same task as classifying Cartan matrices. And let me make this problem even more combinatorial. Instead of classifying Cartan matrices, I'm going to classify Dynkin diagrams, which are certain graphs. So a Dynkin diagram is a graph, which is defined as follows. It's defined, you give me a Cartan matrix and I give you a graph. And the definition is that the Dynkin diagram of, let's say, of a root system phi, or the corresponding Cartan matrix, is so it's a graph with it's a graph gamma with whose vertices correspond to the simple roots. So the vertex set of gamma is just a set of alpha 1, alpha 2, all the way up to alpha r, or just the integers from 1 up to r. And then and so the edges are going to be, there's going to be multiple directed edges, and aij times aji edges between I and j, where, so this is going to sound weird, but later we're going to see why that's the case. So where if the number of edges is 1, aij times aji is equal to 1, then I just get 1. Then you just get one undirected edge. But otherwise, if this number, well, if this number is 0, then there is no edges. But if it's bigger than 1, then I get, then the edges are, then all this many edges are directed from, so I need to choose a direction, directed from I to j, where the root of alpha I is longer than the root alpha j. Or in other words, where aij is the entry in the row I is smaller than the entry in row j, I think. And so that's the condition, right? So you have a graph. Usually it has just a single undirected edge between pairs of vertices, but sometimes if your pair of roots forms so any pair of roots forms a root system of rank 2. And so it's going to be either one of A2, B2, or G2. So if it's A2, then it's a single edge. If it's B2, then it's a double edge directed from like this guy to this guy. And if it's G2, then it's a triple edge directed from this guy to this guy. Now here is a picture which classifies all crystallographic root systems. So you can see there is AN, BN, CN, DN. There is 4 infinite families. I'm going to define them explicitly as collection of roots later. But then there's also 3 exceptional cases. So this index n here is always the rank, which is the number of simple roots. So an has n vertices. The corresponding Dynkin diagram has n vertices. All right. And so in type B and C, you can see that there is a double arrow at the end, right, which corresponds to this a subroot system, which looks like this. And in type G2, as we saw, G2 is that picture with the 12 arrows. You have a triple arrow in the Dynkin diagram. And there is also some exceptional stuff, which are kind of very nice pictures in higher dimensional space, completely symmetric. It's interesting that you get these 4 exceptional cases. You know, I give you a definition of root systems, and then the classification is very non-trivial. It involves 4 infinite families and a bunch of exceptional ones, which are, yeah, they have nice applications. And the corresponding, yeah, so for example, let me try to draw the Cartan matrix for type A. So the Cartan matrix looks like this. It has 2, 2, 2, 2 on the diagonal, and then the super diagonal has -1, -1. So these -1s, they correspond to the edges. They correspond to these edges between adjacent vertices. And then there is 0 everywhere else. And similarly, you can reconstruct the Cartan matrix from the Dynkin diagram uniquely using these conditions. All right. So again, as I said, I'm gonna define these root systems later. For En and F4, you can check the Wikipedia page. There's a complete description. I always go there to remind myself. But for now, let me also mention a related problem, which is I want to classify not root systems, but Coxeter groups. So remember, the Coxeter group, it doesn't really care about the reflection group doesn't really care about the length of your roots. Right, it's just, so in other words, reflection groups correspond to all root systems, not necessarily the crystallographic ones. And those also admit a nice and very similar classification. So let's say W is a Coxeter group. So it's of the form Si for I, where I goes from, let's say, 1 to R, and then you have the relations. And to that data, I'm going to associate the Coxeter graph. Coxeter graph. Let's say I'm going to denote it by G. So it's going to be slightly different than the Dynkin diagram. The vertex set is still going to be your set of simple reflections, just integers from 1 up to r. And then, by the way, we don't label the vertices of our Dynkin diagram because remember you can permute the entries of permute your simple roots, and then the labels are going to get permuted, but the graph is going to stay the same. Okay, so the vertices are just integers from 1 up to r. They correspond to these simple transpositions, and then the edges, unlike the case of the Dynkin diagrams, the edges are all undirected, but some of them are going to be labeled. So the conditions are that if you have mij equal to 2, so if mij is equal to 2, then SI_SJ is equal to SJ_SI. So it means that SI and SJ commute. SJ_SI. And in this case, I just put no edge between I and J. So the corresponding two roots are orthogonal and not connected by an edge. If mij is equal to 3, then you have this braid relation. SI_SJ_SI is equal to SJ_SI_SJ. And in this case, I'm going to put a single unlabeled edge between I and J. And finally, if mij is bigger, so it's 4, 5, all the way up to infinity, including the infinity, then I'm going to put an edge between I and J, still undirected, labeled by mij. So some edges are going to be labeled by integers 4, 5, up to infinity, corresponding to these kind of more complicated relations. Here is a picture. I'm going to put them side by side. The classification, oops, I guess. Okay. So on the one hand, I'm going to have the classification of Dynkin diagrams or crystallographic root systems as we had before. But on the right hand side, I'm going to on the right hand side, I'm going to put the classification of Coxeter graphs, or in other words, the classification of Coxeter groups. So you can see that the classifications are very similar. AN corresponds to AN. Now one difference is that BN and CN are only going to be different, only going to have different lengths of the roots, which corresponds to changing these arrows. And both of them are going to correspond to the Coxeter graph, where you just have an edge labeled 4. It's undirected. And then the type D corresponds to type D. It's the same. It's kind of crazy that these two classifications are so similar. EN corresponds to EN. Now, the only kind of new stuff you get is H3, H4, and these. So I2 is the dihedral groups. I2 is dihedral groups. Right, so they all correspond to root systems in the plane, where your roots are the vertices of an irregular 2n gun. And in this case, the edge is labeled by K. And there are some special, right? So for example, here I have G2. G2 is a special case of the dihedral group. And the same stuff goes for like A2. Yeah, let me write down. I have these coincidences here. So I2 of 3. So when an edge is labeled by 3, then it's unlabeled, and that's actually just A2. When I2 of 4 it corresponds to, like, instead of a hexagon, you get an 8-gon, an octagon. So that's type B2. finally I2 of 6, that's type G2. So you can see that the two classifications are, so on the right hand side I'm basically classifying root systems without the crystallographic condition, and I don't get any much more stuff. I get some kind of new groups, but not too many. And so you can kind of, at this point, you can forget about all the root system business, and you can just remember these. So these are the important pictures. They show up throughout mathematics unexpectedly in many ways, and one of them is going to be cluster algebras. Now let me finish by explaining these. What are these root systems A, B, C, D? These are called root systems of classical type. And so I have a picture of the three-dimensional ones. And so the description is that for a n minus 1, you have all roots of the form ei minus ej, where I always assume that I is not equal to j. So you just take all possible differences like this, as we discussed previously, and then you get a root system of type a n minus 1, right? Because so the index is always the dimension of the span of your root system. In this case, it's n minus 1 dimensional. I and j go between 1 and n. For bn, well, let me start with dn, because that's actually going to be contained in the rest of them. dn, the roots are plus or minus ei, plus or minus ej. Well, that's it with the same condition that I and j go between 1 and n. And so you can see the picture of d3 on the right here, and basically for any ei and ej, you get a point like ei plus ej. Or if you choose minus ei, then you're going to get this point, and etc. You get all these midpoints of edges of the cube. Now for bn, you take dn, ei plus minus ej, and you also add plus or minus ei for all I between 1 and n. And that's the picture on the left. So you see it's a union of dn together with the basis vectors. Oops. Together with the plus or minus basis vectors. And finally, so bn and cn, as I mentioned, only differ in the lengths of some roots, plus or minus ej, and plus or minus twice ei. So you can see here, C3 is obtained from B3 by just rescaling the basis vectors, taking twice the basis vectors instead of once the basis vectors. Now, an exercise for you is to compute the, let's say, the simple roots of these root systems, and then check that the Dynkin diagrams are of this form. So in other words, it's pretty easy to kind of construct them all, and they correspond to the SLN or SO, like the orthogonal group, the symplectic group. Like type B is the odd orthogonal group, type D is the even orthogonal group, etc. So these kind of correspond to classical Lie groups, but there are also these exceptional Lie groups. And so in the next lecture, I'm going to explain how to connect all this stuff to cluster algebras. And thank you very much. The next lecture is going to be pre-recorded, and I will see you all on Wednesday.